yesterday we were talking about a charged particle in a homogeneous magnetic field, and I said I will take the field along the z direction. So, today we will continue with that problem of a charged particle of mass m subject to a uniform magnetic field and as I mentioned to you yesterday, the eigenfunctions would involve the eigenfunctions of the oscillator type, of the linear harmonic oscillator type, and also a part of the eigenfunction would correspond to that of a free particle, and we will see how exactly that comes. So, first of all, the magnetic field B itself can be written in terms of the vector potential as del cross A. A is the vector potential, and I said that if I did a gauge transformation where A changed to A plus grad chi, it simply does not change B. So, this is an example of a gauge transformation. In fact, the full set of transformations are best understood if we look at the electric field as well, because the electric field can be written as minus gradient of the scalar potential phi minus 1 by c delta A by delta t, and therefore, it is not enough if A alone made a transformation. In order to keep the electric field unchanged under the gauge transformation, phi changes correspondingly to phi prime, which is phi minus 1 by c delta chi by delta t, the same chi that appears there in the A equation. So, these two define the gauge transformation. The gauge transformation is not a space-time transformation. As you can see, the transformation is made on the vector and the scalar potential, not on space-time. So, it is an example of an internal symmetry transformation, something that does not change space-time itself, but only changes other quantities, in this case A and phi. Now, it is very clear that if A changed in this manner and phi changed in that manner, E is left unchanged, because under the gauge transformation E goes to minus gradient of phi minus 1 by c delta chi by delta t and minus 1 by c delta by delta t. A has changed to A plus grad chi. It is evident that here minus grad phi minus 1 by c delta A by delta t continues to be, and this term 1 by c gradient of delta chi by delta t comes with a plus sign, and here 1 by c gradient of delta chi by delta t comes with a minus sign. Therefore, they cancel out and the electric field is left unchanged under the gauge transformation, even like the magnetic field is left unchanged under the gauge transformation. Chi is called a gauge parameter, and it is clear that any chi will do the trick. There are no particular conditions that I have used on chi except that it is a scalar, and therefore, I have an infinite choice of chi's that I could use. The only feature that I need to remember is this, that if A changes by gradient of a given specific chi, phi should change in this manner using the same chi. Now, under a gauge transformation, therefore, the vector and scalar potentials change, leaving the electric and magnetic fields invariant. So, several choice of A's and phi's can be used. let me look at one of them. So, A could well be minus half y b. I have selected B to be along the z axis. It is a constant here, not a function of space time. So, it is a homogeneous magnetic field, and I have defined that direction to be the z axis. So, A could be this. Now, it is pretty clear that if I look at del cross A, that is simply going to be Ex in general, of course, delta Az by delta y minus delta Ay by delta z plus Ey times delta Ax by delta z minus delta Az by delta x plus Ez times delta Ay by delta x minus delta Ax by delta y. Now, with this choice of the vector potential, since Az is 0, this does not contribute. Ay is not a function of z, so this does not contribute. So, there is no component along the x axis. Similarly, look at this. Ax does not have z in it, and therefore, this does not contribute, and Az is 0. So, there is no component along the y direction. However, delta Ay by delta x, so the only non-zero term, non-vanishing term is along the z direction, and I have half b, and then from here I have another half b. So, that just gives me a b Ez. So, this is a possible choice of A, and in fact subsequently during this lecture I will work with this choice of A. But this is not the only choice. Clearly, I can have another set of components for A. I could choose A to be minus yb 0 0. Now, if I did this, it is clear that del cross A is again b Ez, can be easily checked out. So, it is possible to choose this set or that set for A, but then these two would differ by a gauge transformation. As you can see, originally A was minus half yb, and that has gone to minus yb, and therefore, grad chi the x component would be delta chi by delta x. Delta chi by delta x is minus half yb. Similarly, half xb, that was Ay, went to 0. Therefore, delta chi by delta y is minus half xb, and Az was 0 anyway. So, it is possible that I can choose chi to be minus half xyb. That is a possibility for chi, because surely delta chi by delta x gives me that, and delta chi by delta y gives me minus half xb. So, these two sets that I have selected for A are related by a gauge transformation. It is also possible to choose Ax to be 0, Ay to be non-zero, and Az to be 0. Any one of these is a possible choice of gauge. So, when I say that I have chosen a gauge, it means that I have already selected my components Ax, Ay, Az, and those are the components with which I am going to work. The freedom that I have is called gauge freedom, the freedom to choose any one of these infinite sets, each one related to the other by a suitable gauge transformation. In other words, by a specific choice of the parameter chi. So, in general, one works with any choice of gauge. A popular gauge is the Landau gauge, where two components are 0 and the third component is non-zero. So, that is a possible choice, but as I have said, I would work with this choice for A in the latter half of my lecture. But now let us get back with this introduction to the charged particle in a homogeneous magnetic field. And as I pointed out in the last lecture, there is a minimal coupling prescription, P goes to P minus EA by C. And this object I refer to it as script P, capital P. The Hamiltonian itself therefore was P squared by 2m. Originally it was little p squared by 2m, and that has now become script P squared by 2m. So, Px is Px minus E Ax by C, and so on. Py is Py minus E Ay by C. Pz is little pz minus E Az by C. The point is the following: when I do a P squared, it obviously involves Px squared, Py squared and Pz squared. In terms of the linear momentum of the particle, it would involve the square of the linear momentum of the particle and also the square of the vector potential. So, I have little p squared and little a squared in the Hamiltonian when I expand it. There are no cubic terms. Of course, there are cross terms. There would be a p dot a kind of term and an a dot p term and so on. I understand, however, that I am dealing with a quadratic form. I am dealing with terms which only involve quadratics in p and a, or cross terms p dot a and so on, and therefore that rings a bell. Is it possible to somehow choose variables such that this problem gets mapped on to the linear harmonic oscillator problem, because I know that I have dealt with the quadratic form of the Hamiltonian there, and since I know the energy eigenvalues and the eigenfunctions for that problem, would it be possible to use that in understanding what the energy spectrum of the charged particle in a magnetic field is? So, that is the question that we will address here. In order to do that, I first of all have to find appropriate canonically conjugate variables. You will recall that in the harmonic oscillator problem, we had the commutator between x and p sub x if you wish, because it was a linear harmonic oscillator. The commutator between x and p was IH cross. So, my first job here is to identify two such objects pertaining to this problem where the commutator is IH cross. Then, even as I combined x and p, I had x plus IP barring some constants and x minus IP, it is a Hermitian conjugate. Those were the ladder operators. So, here too, if I can find such ladder operators, my job is done. So, my first problem here is to find out various commutators. So, in that spirit, I first wish to find the commutator of Px with Ay. Now, that is an easy job. I work in the position representation because Ax, Ay, etc. are functions of x, y and z. So, Px Ay psi is minus IH cross delta by delta x of Ay psi. Right now, I do not have a choice for Ay. I work with a general A minus of Ay minus IH cross delta by delta x psi. So, this object is minus IH cross delta Ay by delta x times psi minus IH cross Ay delta psi by delta x plus IH cross Ay delta psi by delta x. So, this is the same as minus IH cross delta AY by delta XI, and therefore, the commutator PXAY is minus IH cross delta AY by delta X. Clearly, this is a cyclic relation in the sense that if I take PY commutator with AZ, I will have minus IH cross delta AZ by delta Y. Similarly, PZ commutator with AX and so on. So, this is the first thing that I have. Now, my aim, since the Hamiltonian is in terms of capital P's, the next step is to use this to find out the commutator of capital Px with capital Py. Now, this would mean the commutator of Px minus E Ax by C with Py minus E Ay by C. Surely Px and Py commute with each other, and I already know the commutator between Px and Ay, even as I know the commutator between Py and Ax. So, this quantity is simply going to be minus E by C commutator of Px with Ay plus E by C commutator of Py with Ax, because the commutator of Ax with Py is minus the commutator of Py with Ax. So, I can now substitute and find out what this is. I therefore have commutator of Px with Py is minus E by C minus IH cross delta Ay by delta X, that is the first term, plus E by C minus IH cross delta Ax by delta Y. So, that is the same as IH cross E by C. I have delta Ay by delta X minus delta Ax by delta Y, and that is Bz. As I said, right now I have not assumed it to be along the z direction, the magnetic field to be along the z direction, but Px Py is IH cross E by C Bz, which means that it should be possible for me to scale things here. I should be able to decide, I should be able to give appropriate values for scale Px and Py in such a fashion that I simply get IH cross as my answer. And that is what I would try to do now, because if I have root of C by E, let us now say that B is Bez. Therefore, I will just call this B instead of Bz. So, if I take root of C by Eb Px commutator with root of C by Eb Py, that is simply going to be C by Eb commutator of Px with Py, which I know is this object. There is an identity operator there, but by now we know that we do not have to put it in, but it is there. And therefore, this is the commutation relation that I have, which is analogous to the commutator of X with P. So, I have root of C by Eb Px, root of C by Eb Py is IH cross identity. So, my hunch was right. It should be possible now to define ladder operators, appropriate ladder operators, I will call them B and B dagger, as linear combinations of Px and Py, which satisfy the algebra commutator B with B dagger is identity. So, I go about it this way, as in the case of the linear harmonic oscillator. I define a B which is 1 by root of 2H cross root of C by EB Px plus I root of C by EB Py. Therefore, B dagger is 1 by root of 2H cross, the dagger of this, the complex, the Hermitian conjugate. Now, in the commutator B with B dagger, therefore, it is clear what is going to happen. So, the commutator of B with B dagger is simply identity, because this will pull out an overall factor. In the commutator of B with B dagger, I get an overall factor 1 by 2H cross. There is a commutator which is C by EB, root of C by EB Px with minus I root of C by EB Py, and I have got that commutator here. That is an IH cross already. With this minus I, it gives me a plus. Similarly, out here, that gives me the same value IH cross with a plus, and therefore, there is a 2 which cancels out with the 2 that comes out as the overall coefficient. It is a trivial matter to check that BB dagger is identity, and that is good news for me, because now all I have to do is find out B dagger B. So, if I expand B dagger B, it is 1 by 2 H cross root of C by EB Px minus I root of C by EB Py, these are all capital P's, times root of C by EB Px plus I root of C by EB Py. That is 1 by 2 H cross. The first term is just C by EB Px squared, and this times that gives me plus C by EB Py squared. Then I have cross terms. The first thing is plus I C by EB Px Py, and the next one is minus I C by EB Py Px. But that is clearly a commutator. I can write this as 1 by 2 H cross C by EB Px squared plus Py squared plus I commutator of root of C by EB Px with root of C by EB Py. I already know what that commutator is. We have got that here. Root of C by EB Px commutator with root of C by EB Py is merely IH cross. Therefore, I can substitute IH cross there. What do I get then? My final answer is quite simple. Let me write that here. So, I was trying to figure out what B dagger B was. That is 1 by 2 H cross Px squared plus Py squared. There is an overall coefficient C by EB multiplying that, and then I have plus I times IH cross, which is minus H cross, and therefore C by 2 H cross EB Px squared plus Py squared. Suppose I pull that out, minus EB by C H cross minus EB H cross by C equals B dagger B. I can do better. I can pull the 2 inside and multiply this by 2, divide this by 2, and then I am through, because I now see that B dagger B plus half times EB by H cross C is Px squared plus Py squared by 2. What I want is Px squared plus Py squared by 2m, and therefore this is simply going to be EH cross by MC, B dagger B plus half times EH cross by MC. E and H cross went up there, so EH cross by MC is Px squared plus Py squared by 2m. And so it is clear that this is of the harmonic oscillator form. EH cross by MC, there is a B, of course, that is Px squared plus Py squared by 2m. A part of the Hamiltonian has therefore been written in terms of something analogous to the harmonic oscillator Hamiltonian. But remember that the total Hamiltonian was Px squared plus Py squared by 2m plus Pz squared by 2m. But Pz is little pz minus EAz by C, but since Az is 0, Pz squared by 2m is simply replaced by little pz squared by 2m. You should remember that this is an operator, it is not a number, this is a Hamiltonian, it is an operator pz squared by 2m. But therefore the Hamiltonian can be written in a very easy form as B dagger B plus half times EH cross by MC B plus Pz squared by 2m. And this is an easy thing for me to handle, because I certainly know the eigenspectrum of this part. It is n plus half H cross omega, where n takes values instead of H cross omega. Now I will write EH cross by MCB. This is n plus half EH cross by MCB. That is going to be the eigenvalue. For a given value of B, I have a set of discrete energy levels, each labeled by the values of n taking value 0, 1, 2, 3, etc. And this is precisely the Hamiltonian for a free particle, and I know the solution for the free particle Hamiltonian. I know the solution for the eigenstate of the free particle Hamiltonian. So which is what I will now use. I have the following solution. The energy eigenvalue En is n plus half EH cross by MCB, n taking value 0, 1, 2, 3, etc., plus the eigenvalue of the operator Pz. First of all, this is a free particle Hamiltonian, and therefore I have the number P, which is the eigenvalue of the operator Pz. Pz acting on psi z is little p psi z, and that little p is what figures here. Psi of z itself is a plane wave solution, e to the I Pz by H cross. So the linear momentum of the particle is p. There is a plane wave solution, it behaves like a free particle with a constant linear momentum along the z direction, e to the I Pz by H cross is the solution. And as far as psi x y is concerned, that is the eigenfunction corresponding to this discrete spectrum, I know that the solutions are the harmonic oscillator solutions psi n. It is clear that psi 0, the lowest state, will be an eigenstate of the operator B with eigenvalue 0, trivial eigenvalue 0 psi 0. this is like the ground state of the harmonic oscillator, and therefore I write B psi 0 is equal to 0, and then I create the various excited states by repeated application of B dagger. So I repeatedly apply B dagger n times to psi 0, that gives me psi n, and for the sake of normalization I divide by root of n factorial. So this is what I have. So these are the eigen values, and the eigen functions can be given as the eigen functions can be written out here, because we will do some work with the eigen functions now. So psi is psi of x y, which I call psi n of x y, because it is in the x y plane, and along the z axis I have e to the I p z by h cross. It is usual to normalize that with a root 2 pi. Now how come a plane wave solution like say e to the I p x, pick up a factor 1 by root 2 pi. Consider this. There is a simple way of understanding this. We know the following. This object is delta p minus p prime, but of course I can always write this. Suppose I were working from minus infinity to infinity. I can put in a complete set of states like this, because an integral over the allowed space dx ket x bra x is identity, and that is what I have sandwiched here. And I know that this is the wave function. So this would have an e to the I p prime x, and this would have an e to the minus I p x. I have written it in the x representation, but I can use a form of the delta function. This can be written in that following fashion, and then when I compare the two of them, it is clear that I need to put in a 1 by 2 pi on this side, and therefore if I have an e to the I p prime minus p x, there should be a 1 by 2 pi, it is off by 1 by 2 pi, and so each of this, say psi of x, would be e to the I p x by root of 2 pi. So that is how I get the root 2 pi there. So that is one factor which could be put in, but quite apart from that, there is the whole business of normalizing e to the I p z by h cross. It is a plane wave solution. So if you look at psi star psi, where psi is e to the I p z by h cross, and z itself goes from minus infinity to infinity, you can see that this blows up. But plane wave solutions are extremely common in quantum mechanics. The free particle is the simplest example we can think of. So normally, in order to normalize a plane wave solution of this form, e to the I p z by h cross, you take recourse to box normalization. In one dimension, for instance, you imagine that the particle is really moving freely within a box, let us say size L. So the box goes from minus L by 2 to L by 2. In that case, if you started with e to the I p z by h cross by L to the power of half, it is clear that this is normalizable. If this is the wave function, start with some psi by L to the power of half, integral minus L by 2 to L by 2 psi star psi dz or dx, whichever be the direction, the axis on which the box is. Then you find that if this cancels out, if e to the I cancels with e to the minus I, you are left with a 1 by L, because that is the way you normalized it, and dx when integrated gives me an L, and that gives me a 1. So really it is common in the normalization in the box normalization to start for every dimension you divide by root L, and therefore in 3 dimensions the wave function is down by L to the 3 by 2. So L to the minus 3 by 2 times the wave function is what you could use if you were doing an integration like this in 3 dimensions. So this box of course is, I've done it for 1 dimension, otherwise x, y and z go from minus L by 2 to L by 2, and in each case you pick out an L to the minus half, and therefore the box normalization involves dividing by L to the half, dividing by L to the half for each dimension that you look at. Then you do the problem, do the problem of a free particle inside that box, finally take the limit L going to infinity. And clearly the limit of a function is not the same as the value of the function at that point, and that is precisely how the box normalization is done in the case of a plane wave problem. But that is as far as the normalization is concerned. The structure itself is this. This, as you will recall, this part psi sub n of x comma y would involve the Hermite polynomials. You will recall that the ground state of the harmonic oscillator was a Gaussian function. So I would expect a Gaussian for psi 0 of x y. I would expect a Gaussian function of x and y if n is 0. So it is certainly worth looking at what happens to the ground state psi 0 of x y. The energy eigenvalues of course are n plus half E h cross b by m c plus p squared by 2m, n taking value 0, 1, 2, etc. And those are the energy eigenfunctions. Have to normalize it suitably. Now let us look at a specific choice of A. We have already said that B is along the z axis. In other words, I choose the direction of B to be the z axis, and I wish to work with the choice. So I am going to choose A to be minus half yb, half xb, 0. These are the components of A. Want to look at the ground state solution and look at the Gaussian form, get back the Gaussian form. So I have b psi 0 of xy equals 0. Even to begin with, I realize the following. Since B is along the z axis, there should be a cylindrical symmetry in this problem. Even in the classical analog, when we look at a charged particle moving in the presence of a homogeneous magnetic field, it is helical motion, and therefore there is circular symmetry. There are planes where there is a symmetry. So I would expect to see that kind of symmetry in my solution. I now have to write down B, which I already have. B was defined as 1 by root of 2 h cross capital Px plus Ipy, and that object was root of C by Eb Px plus I root of C by Eb Py. So this was my definition of B. Since this was the manner in which we had defined B, let us now recall that Px is little px minus Eax by C, and Py capital was little py minus Eay by C, and substitute for Ax and Ay accordingly, and then you have B equals 1 by root of 2 h cross root of C by Eb times Px minus E Ax by C plus Py I times Py minus E Ay by C. Substitute for Px as minus IH cross delta by delta x, similarly for Py, and use the values of Ax and Ay that we have selected. In other words, we are using a specific gauge now, and therefore B would simply be root of C by 2H cross EB times minus IH cross delta by delta x minus E by C, Ax is minus half YB plus I times minus IH cross delta by delta y for Py minus E by C half XB for Ay. So this is what we have. This quantity is simply root of C by 2H cross EB times minus IH cross delta by delta x plus EYB by 2C plus H cross delta by delta y minus IEXB by 2C. So this is what we have when we expand this. It's good to change variables and also absorb constants suitably. I define a constant lambda, alpha if you wish, which is root of EB by 2H cross C. Now if you did that, you define a variable zeta which is alpha x and eta which is alpha y, so that I can get rid of unnecessary constants. So you see the first term, for instance, the x would be replaced by zeta by alpha, and I'll have delta by delta zeta instead of delta by delta x, and delta by delta eta instead of delta by delta y. With this replacement, it's a simple matter to rewrite this equation in terms of zeta and eta. So in terms of the variables zeta and eta, what do I get for the differential equation? The equation is simply that B acting on the ground state is 0. It's the annihilation operator on the ground state. So I have, apart from a minus I by 2, delta by delta zeta plus zeta, if I recast the equation in terms of zeta and eta, plus I times delta by delta eta plus eta. This acts on the wave function, which is a function of zeta and eta now, and I'd like to do that in terms of a separation of variables. I will write the wave function of as f of zeta g of eta, and then this operator acting on that wave function is 0. So I basically have delta by delta zeta plus zeta f of zeta g of eta plus I delta by delta eta plus, that is eta not zeta, f of zeta g of eta equals 0. As we always do in separation of variables, let me divide by f of zeta g of eta. So basically I have g of eta by f of zeta g of eta, delta by delta zeta plus zeta acting on f of zeta. I have pulled the g of eta outside because this is only an operator function of zeta and cannot act on g of eta. And similarly here, I can write this in the following manner. like I always do when I separate variables. So that just tells me that 1 by f of zeta delta by delta zeta plus zeta f of zeta plus I by g of eta delta by delta eta plus eta acting on g of eta equals 0. So this is merely a function of zeta, and this is going to give me a function of eta. And if this equation has to be true, this should be equal to some separation constant. I'll call that lambda. So this is lambda and this is minus lambda, and therefore they cancel out, which therefore means, in terms of the separated equations, delta by delta zeta plus zeta minus lambda acting on f of zeta equals 0. That's my first equation. And similarly, delta by delta eta plus eta minus I lambda. There's an I there, and I have to take care of that. Acting on g of eta equals 0. What is the solution? The solution is simple. Now I have psi 0 of zeta eta. And I've written the 0 there to show that we're discussing the ground state wave function. These are Gaussians. So the solution is e to the minus half zeta squared from there. But that's not all. There is a lambda, and that's going to give me an e to the minus lambda zeta, e to the minus half eta squared, e to the minus I lambda eta. That is the solution. Apart from constants, overall constants, normalization, let's not worry about that. You have this. Essentially, you have this. So basically, I'm not worrying about overall multiplicative constants and so on, but this is what I have. And this can be written as e to the minus half zeta squared, e to the minus half eta squared, e to the minus lambda zeta plus I eta. I will comment about this a little later, but I can also write this if I complete squares and so on. Suppose I write lambda, which in general can be complex. This is a well-behaved function even if lambda is complex. So if I write this as some zeta naught plus I eta naught, write it in terms of its real and imaginary parts, then this psi can be written also as e to the minus half zeta minus zeta naught the whole squared. It's a shifted Gaussian, e to the minus half eta minus eta naught the whole squared, and e to the I zeta naught eta plus eta naught zeta. I leave it to you as a simple exercise to put it in this form. So I could think of it, the solution could be written this way or that way, and again I have not worried about normalization, overall constants and so on and so forth. So this is what I have. Now a variety of comments can be made on the solution. First of all, since this is what comes out of the xy plane, because you will recall that zeta and eta were functions of x and y, it would essentially involve x minus x naught the whole squared and e to the minus half y minus y naught the whole squared. Of course, as far as z is concerned, there is an e to the I pz by root 2 pi, that stays. So the full solution has, apart from all these things, it also has an e to the I pz by root 2 pi, which we have discussed earlier. So now if you look at the xy plane, the solution only depends on the distance x minus x naught the whole squared, that distance from x naught comma y naught. So there is a circular symmetry that you see in this problem. One would expect it, because I know, for instance, that once I map it onto the harmonic oscillator, as far as the ground state is concerned, it's a Gaussian. This turns out to be shifted by x naught and y naught. And the x naught and y naught came because the separation constant was written in terms of zeta naught and eta naught, which were related to x naught and y naught. And then you see the circular symmetry in the xy plane, which is a sort of vestige, if you wish, or very consistent, if you wish, with the classical situation where in the presence of a magnetic field you have circular trajectories. So that's one thing. An interesting observation is the following, that if you look at this term here, this is an exponential series, and so I can expand it in powers of this exponential series can be expanded in powers of zeta plus I eta to the power of s. There are an infinite number of terms, and they will involve zeta plus I eta to the power of s, where s takes value 0, 1, 2, 3, 4, and so on. And those are all linearly independent objects. I could choose any one of them in the solution, and therefore I have an infinite degeneracy even in the ground state. So if I take a circular section in the xy plane, there is an infinite degeneracy, because for any value of s, 0 or 1 or 2, I have one solution, and all those solutions are linearly independent. The series is expanded in terms of this. These are called the Landau levels. That means that while it looks like the harmonic oscillator solution in the xy plane, even the ground state is infinitely degenerate. And the levels are called the Landau levels. To summarize, we have very many interesting features in this problem of the charged particle in the presence of a homogeneous magnetic field. There is a discrete spectrum. The eigenvalue is n, n taking value 0, 1, 2, 3, apart from the plus half and the constants that are analogous to h cross omega in this problem. But then there is also a continuum in the z-axis, because p takes, the momentum takes a constant value and any value at that. It's a plane wave solution. Infinite degeneracy even in the ground state. A circular symmetry which is reminiscent of what one sees in the presence of a magnetic field in a classical context. And these are the take-home lessons, because the spectrum is continuous along the z-axis and discrete in the xy plane.